So today we're going to prove what I called Theorem A in the first lecture. So this is a criterion for elliptic curves over Q not to have n torsion. So let me remind you what the theorem says. So I'm going to call this Theorem 1. I'm going to state 3 theorems in this lecture. So it says that, suppose that you have a prime number n that's greater than 7. And suppose that there exists an abelian variety, A over the rational numbers, and a map of varieties, F from x0n to A, such that the following 3 conditions hold. So first is that A has good reduction away from n. The second is that A has rank 0. The Mordell V group of A over Q has rank 0. And the third is that F separates the 2 cusps of x0. F of 0 is not equal to F of infinity. The conclusion then is that no elliptic curve over Q has a rational point to order n. Are there any questions about the statement? Okay, this is what we want to, following this lecture, what we're going to try to do is verify the hypotheses of this theorem, construct an A and an F like this, so that we can prove Mazur's theorem that elliptic curves don't have n torsion if n is a prime bigger than 7. And so the hardest part of the hypotheses is this one. Did I not write the S there? That has good reduction. So this is the hardest hypothesis to verify. And we had another theorem, we called it Theorem B in the first lecture, that told us how we could guarantee that. So combining the 2 theorems, the criterion for rank 0 and this one, gives you the following theorem. And I'll just write it out just so we remember what all the hypotheses are. So Theorem 2, it's just the combination of this one and the previous one. N greater than 7 is a prime, and P is a prime different from N. So suppose there exists A over Q in abelian variety, and F a map like 0n to A such that the following conditions hold. So first, A has good reduction away from N. Second is that A has completely toric reduction at n. The third is this condition on the p torsion of A as a Galois representation. So if you look at the p torsion of A and its q bar points, this is a representation of the absolute Galois group of Q. And we want its Jordan-Holder constituents to all be one-dimensional and either trivial or cyclotomic. So the Jordan-Holder, well, this thing has Jordan-Holder constituents, either trivial or the cyclotomic character. And f of 0 is not equal to f of infinity. Okay, so if you have this, then same conclusion. So following today's lecture, this is what we're going to concentrate on, constructing an A satisfying these conditions. All right? So you should remember those things, write them down in your Okay, but today we're going to prove theorem 1. So we're actually going to prove, most of the work is going to be in proving a slightly different statement, which I'm going to call theorem 3. So let me see what that is. So let A and F be as in theorem 1. And suppose that you have an elliptic curve with a point of order n. Then the n torsion of E as a group scheme over Q, or as a Galois representation, is just z mod nz plus mu n. And so note, remark, saying that you have a point of order n, so point of order n implies that you have a z mod nz inside the n torsion. That's exactly what it means to have a point of order n. And then the Weil pairing says that the quotient has to be mu n. That means that the n torsion is an extension. Z mod nz is the sub, and un as the quotient. And theorem 3 is just saying that this extension is split. Okay, so first I want to explain why theorem 3 implies theorem 1, and then we'll prove theorem 3. So of course we're going to proceed by contradiction, because theorem 1 is saying that no such elliptic curve with a point exists, and theorem 3 is saying something about if you had such a hypothetical thing. And basically the idea is, if you had a E over Q with a point of order n, then by this theorem you would get a mu n inside of the n torsion. And so you could quotient by that mu n, and then your point of order n would give you a non-trivial point of order n on the quotient, and you could keep applying this. So you'd get this series of things, and you just show that that can't happen. Okay, so let me do the details of that argument now. So 2 lemmas to begin with. So this lemma is under the assumption that you have an A and an F, as in theorem 1. And it's just that x0 of n of q and x1 of n of q are finite. So excluding, there's finitely many n where these curves have genus 0 and genus 1. And excluding those, this statement is a special case of the Mordell conjecture, which is proved by Faltings. But Maser proved this in his paper before Faltings proved the Mordell conjecture. So this was a kind of special case that was established first. But the proof is really easy in the situation that we're in. So you have, maps. x1 of n maps down to x0 of n. And this maps by our f to a of q. And each of these maps has finite fibers. That's just because x0 and x1 are curves, and each of the maps is non-constant. It's just always true for non-constant maps from curves. And then by hypothesis, a of q is finite. So that does it. Yeah. No. Sorry, this lemma is true when you have an A and an F. Yeah, no, it's not true because these curves can have genus 0. And then in those cases, they'll have infinite limit rank. Right. I don't know. I don't know offhand. Do you know, Kartik? In Maser proves that if there's this certain quotient of J0 and that he calls the Eisenstein quotient, and that its more Delve group is always finite. But I don't know. Just don't remember for like x down to 11 for the small cases. Yeah. Right. All right. So the second lemma we need is just that if E is an elliptic curve over Q, then its endomorphism ring is Z. So the point of this is that you might have CM, might be a CM curve when you go up to C or some algebraic closure of Q, but none of those extra endomorphisms are actually going to be defined over Q. And so here's the proof. So let O be the endomorphism ring, and let K be O tensor Q. So we know that this K is either Q or an imaginary quadratic field. Well, we proved that, and we proved that just by considering what happens over the complex numbers and thinking about C mod a lattice and what the endomorphism ring could be. So there's a natural map from O to the endomorphisms of the tangent space at 0 of E, because every endomorphism of E preserves the identity. So it's going to act on the tangent space. And this thing here, I mean, the tangent space at 0 of E is a one-dimensional Q vector space. It's Q. So the endomorphisms of it is Q. And this is a ring homomorphism. So this gives us a ring homomorphism from K to Q. And that implies that K is equal to Q. And therefore O is Z. Okay? Okay, so now we're going to prove that theorem 3 implies theorem 1. Okay, so the idea is to go by contradiction and suppose that we have an elliptic curve. I'm going to call it E1. It's an elliptic curve with a point P1 of order n. Okay, so then theorem 3 implies that there's a mu n sitting inside of E1. And I'm going to define E2 to be the quotient. And P2 to be the image of Q1. Okay, and now you can continue. And so you get E1 going to E2, to E3, going on forever. And here you have a P1, and the image here is P2, and the image here is P3, and so on and so forth. Each one of these things is an isogeny of degree n. And none of these P's are killed by these isogenies. So just keep taking the image of P. So each one of these things, EI, PI, defines a point, a rational point on x1 of n. And since this set is finite, eventually there has to be some sort of repetition here. So 2 of these E's must be isomorphic. So. Let me take J to be bigger than I. So let F be the isomorphism. And let G be the map that you get just by going from EI continuum. Be mapped from over there. Okay, so now we can build an endomorphism of EI by first doing G and then doing F inverse. So this is an isogeny, and it has degree, well, F's an isomorphism, so it has degree 1. And the degree of G, well, you're just doing these n isogenies on j minus I times, so it has degree n to the j minus I. And so the claim is that this is not multiplication by an integer. So if f inverse g were of the form multiplication by n for some integer n, then you would need n to be n to the j minus I over 2 by degree considerations. And so this is just some power of n. And so then f inverse of g applied to pi would be n to the j minus I over 2 pi, which is 0. Because pi is n torsion. Each one of these are n torsion points. But we know that g doesn't kill pi in S an isomorphism. Okay, so that means that f inverse g is not of the form multiplication by n, and so the endomorphism ring of EI is not equal to z. And that's a contradiction. So that contradicts our assumption that we have an E1 and a P1, right? So that means that no such elliptic curve and point exists. Okay? Any questions? All right, so we'll prove theorem 3 now. Okay, so let me write our running assumptions over here so we don't remember. So we have a map F from x0 n to a. And we're assuming that a has good reduction away from n. And a of q has rank 0. And that f of 0 is not equal to f of infinity. And then we're going to fix an elliptic curve E. And P is going to be a point of order n. So our goal is to show that the n torsion of E is z mod n z plus mu n. Right? That's what we're trying to prove, starting with this. Okay, so I'm also going to let this kind of script E over z be the Néron model. And script P be the z point of the Néron model coming from P. Okay? So the proof is there's going to be 4 steps to the proof. So the idea, I mean, we're trying to show that this sequence, z mod nz, en, to mu n splits. I want to show that this exact sequence splits. And what we're going to do basically is show that locally, all the kind of the bad places, it's split. And at the good places, it's kind of an easy thing to understand anyway. And so, in other words, the local behavior of this extension is going to be very nice. And then we're going to apply a theorem from number theory, just kind of a purely number theoretic statement, this Herbrand's theorem. It says that these local conditions force this to split globally. That's the idea. So the main work is going to be in kind of local considerations. Okay, so the first step is that E has semi-stable reduction everywhere. And that's not really going to use this A or the F. This is just a fact about when you have a point on an elliptic curve. It really kind of forces you to have semi-stable reduction in most places. Okay, so the proof, well, let's suppose that it had an additive reduction at some prime p. And then we'll consider that p not equal to n and p equal n cases separately. So first, let's say that p is different from n. Okay, so we know that we're looking at our curve over zp, and we have this point of order n. The reduction map on n torsion is injective, right? Because n is prime to p. And so that implies that the specialization of this p mod p is still a point of order n. It doesn't become trivial. So I'm going to write that like this: p over fp on E over fp has order n. Okay, so this E over fp, special fiber of the Néron model, we know something about its component group just by the classification of Néron models. There's at most 4 connected components. So the classification of Néron models implies that this thing has at most 4 components. And so that means that the image of this p in the, yeah. Well, it's just, I think it's just always injective if you're prime to p. I think we proved that. Yeah. So it's injective if you're prime to p, and if n is equal to p, it's injective as long as the ramification, this Renault thing. Okay, so this means that the image of p in the component group is trivial, because the component group is small, and p has order n, and n is a bigger prime. So the image in the component group is 0. That means that this thing is contained in the identity component. But the identity component is GA, right? We're saying it has additive reduction. And this is a contradiction because, I mean, GA is P torsion and our point is N torsion. Okay? so now there's the case when p is equal to n. Okay, so since n is not 2, and we're working over zp that has ramification at x1, we still get this injectivity on the reduction map. So p over fp still has order n. And so by the same reasoning, it has to be the case that p is contained in the identity component of the Néron model. Okay. So now we're going to use the semi-stable reduction theorem. So we can find some finite extension of qp where our curve gets semi-stable reduction. So let k over qp be such that ek has semi-stable reduction. And remember, we can choose this k to have degree at most 6. So and that's because we're working over fp. P is the same as n now, and n is not 2 or 3. This goes wrong in characteristic 2 and 3. So I'm going to let O be the ring of integers in K, and little k be the residue field. Okay, so now I'm going to look at the Néron model of E over O. So let's call that E prime. So the Néron mapping property, so there, right, we know that Néron models don't commute with base change. Right? So this E prime is not going to be the base change of E. But the Néron mapping property says that you get a map one way. So it goes from E to E prime. So we get this map from the base change to E prime, and it's the identity on the generic fiber, not the identity as a map of schemes. I don't think so. I think what I'm about to say is going to tell you that it's not. So what I want to say is that F collapses the entire special fiber of E0, the identity component of that fiber. So F, if I look at the identity component of this thing, then its image in E prime, the special fiber there, is just the identity. And this E0K is GA, so I get a non-proper fiber. So I think that means this map is not proper. Okay, and why is that? Well, reason. This thing is GA, and the identity component of this thing, since we have semi-stable reduction, is either an elliptic curve or a torus. And there's no maps from GA to elliptic curves or tori. Okay, so this map has to be constant, and it's a group map, so it has to have image 0. All right, so let P prime be the O point of E prime extending P. Well, this P prime has to be equal F of P. Why is that? Any ideas? Yeah, I mean, over the generic fiber, these are both just P, right? Because that's the identity in the generic fiber. And you can only extend sections in one way. And now this is a contradiction, because if I look over K now, this f of P reduces to 0, right? So over K, f of P specializes to 0, because f collapses the entire special fiber. And so that means that P prime over K is equal to 0. But we still have this injectivity on the reduction map of n torsion, because our ramification index is at most 6, and n is bigger than 7. So that's why we have a contradiction. N is strictly greater than 7, right? So n minus 1 is strictly greater than 6. So this implies that the reduction map on n torsion is injective. So that means the point, our P prime is non-trivial in the generic fiber and n torsion, it can't specialize to 0. So this is a contradiction. And this contradicts the assumption that E has additive reduction, right? So this proves that it has everywhere semi-stable reduction. Yeah. Yeah, I don't think so. I think we're going to use it again, if I remember correctly. Yeah, so, okay. Looks like in the next step I used that n is bigger than 4. Okay. No, even more. Yeah, we're going to use exactly n greater than 7. Next argument. It's used quite a bit. But this argument, I mean, it didn't use kind of any of the specialness in this setup. And this is a pretty general argument. So you can abstract it a little. And it's just a fact about if you have an elliptic curve over like QP or an extension of QP and some point, and something about the order of the point and the ramification index match up, then that forces the curve to be semi-stable. So this is a good kind of general fact to keep in mind. All right, so here's step 2. So this is about the primes 2 and 3. So suppose P is 2 or 3. Then the claim is that E has multiplicative reduction, so bad reduction at P, and our point P doesn't specialize into the identity component of the special fiber. Proof. Well, okay, suppose E had good reduction. Okay, then this point specializes to a point of order n. But, I mean, assuming that E has good reduction says that this E of FP is an elliptic curve. And that implies that its number of FP points is at most P plus 1 plus 2 root P by the Hasse bound, right? And this is always less than, if you plug in 3 for this, you get something like 7.4 or something or other. So this is less than 7.5. But n is greater than 7, so it's at least 11 because it's a prime. And so this is a contradiction. The point is just that 2 and 3 are too small to have an n torsion point. The curve just can't happen. Okay, so that shows that E has bad reduction, and therefore by step 1 it necessarily has multiplicative reduction. All right, so now we need to have the second part of the statement that P doesn't specialize to the identity component. Well, let's look at that. So the identity component is a one-dimensional torus over Fp. So can anyone tell me what the one-dimensional tori over Fp are? Well, you should be able to name at least one. Yeah, or, well, that's just usually thought of as a finite set. You would say GM is the scheme, right? Okay, so GM. What's the other one? Yeah. That's right. That's right. The norm 1 elements of the quadratic extension. So you can take the restriction of scalars from Fp squared down to Fp of GM. So this group scheme it's Fp points, like you said, it's Fp star. The Fp points of this one are Fp squared star. So this is like a two-dimensional torus, but it has a norm map. So on Fp point, this is the norm map from Fp squared star down to Fp star. And so you can take the kernel of this map. It's a map of algebraic groups, and that's a rank 1 torus. Okay, so these are all the rank 1 tori. Can anyone prove that? Okay, so that's right. So that's the first step. That's right. That's right. H1 of the, okay, so every one-dimensional torus over Fp bar is isomorphic to Gm. So that means they're all twisted forms of Gm. And what he was just saying is that the twisted forms are calculated by H1 of the Galois group, it's the absolute Galois group of Fp, with coefficients in the automorphism group of Gm, which is just plus or minus 1. And the Galois action here is trivial because every automorphism of Gm is defined over Fp. So this is just Ham from the Galois group, which is Z hat, to Z mod 2Z, which is 2. So there's 2 tori over Fp, and these are them. Okay? All right, so what do we know about their points? So Gm of Fp is Fp star, and this has p minus 1 elements. Let me call this guy T. So T of Fp is the norm 1 elements of Fp squared star. And this has p plus 1 elements. So the point is that both of these have fewer than n elements. And since the specialization of P is a point of order n, it can't live in the identity component. Okay. Are there any questions? So this has a corollary, which is that the n torsion of E is what we want. Z mod nz plus mu n over qp, or p being 2 or 3 again. And the reason is that you can just let G inside of En be the group of points that reduce into the identity component. So this is a subgroup of order n. And by what we just proved, it doesn't meet Z mod NZ. The Z mod NZ generated by our P. And so that implies that our En is the direct sum of these two things. So that just shows that Z mod NZ has a complementary space, and it has to be mu n by the vapor. Okay, so now we're going to analyze the bad reduction away from 2 and 3. So suppose we have a prime of bad reduction free, then the specialization of this point is not in the identity component. Oops, not hidden. Okay, so this is where the serious work happens. This is the only place where we use our hypotheses, actually. Okay, so note two things, first of all. So first, again, I mean, this point here is a point of exact order n. Again, because we're reducing mod p, and p is not 2 or 3. If p is not n, then you're prime to n. If p is equal to n, then you're big enough to apply the Renault theorem. And 2, E has multiplicative reduction at p. And this is just from step 1. Okay, so if our p here is actually equal to n, then if you look at E0 fp, fn, you look at its fn points, by what we just computed, this is a torus over fn, so it's one of those two tori that we just talked about. And so this thing either has n plus or minus 1 points, depending on if it's the split torus or the non-split torus. And this is prime to n. So that means that this point can't live inside this group. Okay, so the p equals n case is actually easy. So from now on, we're going to assume that p is not equal to n. All right, so there's 3 points on the modular curve that we are going to care about. So 3 z1 over n points of x0n. So 2 of them are the cusps. So first is the cusp infinity. So remember, these correspond to generalized elliptic curves. And I think the definition of the cusp at infinity that I gave before was the one that Mazur says in his paper, but I think it's actually backwards from the usual convention. So I'm going to try to use the usual convention now. So this is the generalized elliptic curve. That's a 1-gon. So its smooth locus is GM. And the gamma 0 n structure on it is just mu n sitting inside of here. Okay, we also have the cusp 0. And this is a generalized elliptic curve. It's an n-gon. The smooth locus of this generalized elliptic curve is gm times z mod nz. And the gamma 0 n structure is just the z mod nz. So the important thing to distinguish about these two cusps is that in this case, the gamma 0 n structure is contained in the identity component of the generalized elliptic curve, and in this case, it's not. And then the third point of interest is the one defined by our elliptic curve in point P. So I'm going to call that x. That z mod nz is generated by P. And so actually to be precise about how this is a z1 over n point, the point is that we can take the minimal regular model of this E over z1 over n. And we know we proved that has semi-stable reduction everywhere. So that means that the bad fibers are n-gons, right? So that's what happens when you have multiplicative reduction. And so this thing does extend to a generalized elliptic curve. And then you can do this thing where you contract the components that the z mod nz doesn't meet in each fiber. And that will give you one of the actual points on the moduli problem that x0n defines. Okay? Are there any questions about that? Just because of what the definition... Okay, so there's two things that you could say. You could say that this clearly defines a point here of x0n over q, and this is a proper thing, so you can just extend it to z1 over n, right? You could do that. But that doesn't tell you what the interpretation of the point is. So I wanted to actually use the moduli definition of the problem. And the definition of the moduli problem, x0n wasn't the stack. I mean, it was the core space of something, right? And the moduli problem that it defined was generalized elliptic curves with a subgroup of cyclic of order n, that in each fiber, the subgroup should meet all the components. And there was this procedure where if you had a subgroup that didn't meet all the components, you could, in a natural way, contract the ones it doesn't meet to get the right kind of thing. So you just do that contraction thing, and that gives you this point. Yeah. Yeah. Yes, that's right. Well, I mean, every geometric object defines a point. It's just, I mean, the kind of things that can happen is that, I mean, gamma 0 n contains -1. The group gamma is the usual, subgroup of SL2Z. And so that means that, every gamma 0 n structure has a plus or minus 1 automorphism. So there's going to be like quadratic twists of things. And those things are all going to define the same point of x0 n, but different points of the stack. Between... Yeah, I mean, it's just true for core spaces in general. Like the Q points of this are going to be, you take the say, Q bar points of the stack, and then take the set of isomorphism classes which are Galois invariant. And that will be the points of the core space. And in the case of elliptic curves, I think every such thing is actually defined by an elliptic curve over Q. That doesn't always have to be the case, right? But I think in this case, they actually do descend. But just some things get identified. All right? Okay, but we do get this point x. All right, so let script A over z1 over n be the abelian scheme extending A. Right, we assume that A had good reduction away from n, which exactly means that you can extend it like this. And so this map F that we had from x0n to A, since x0n extends to a smooth scheme over z1 over n by the narrow mapping property, this F extends. Okay, a few more little observations to begin with. So the reduction map on the torsion of A, so if I look at the, say, z1 over n points of A, which are torsion, I can reduce them mod p, or let me say mod q, q is some prime. So this map is injective for q not equal to 2. And this is using the Renault thing. I mean, it's automatically injective on the prime to q torsion. And since q is not 2 and we're working over zq, which has ramification at x1, the Renault thing applies and says that it's injective. But now we can just say that the reduction map without tors there is injective because A has rank 0. All points are torsion. Okay, so here's the cool part of the argument. So x and the cusp 0, these are two z1 over n points of x0n. Have the same reduction mod 3. And that's because we showed that the curve E has bad reduction at 3, and the level structure didn't land in the identity component. Right? And that corresponds to the cusp 0. So this means that if you look at f of x, this is equal to f of 0 in A of f3. Just because the diagram commutes. I mean, you can apply f and then reduce, or reduce and apply f. And so this implies that x is equal to 0 in A of z1 over n, because the reduction map is injective. Sorry, f of x equals f of 0. That's what I want to say. So that's very strong, right? I mean, we use the fact that 3 was very small to kind of fit things to, force things to happen in a certain way. And then this rank 0 hypothesis just implies that what's going on in mod 3 determines what's actually going on over z. That's kind of the magic of the argument. Okay, so now, remember, what we're trying to prove is that we have this prime p of multiplicative reduction. We want to show that our point script p doesn't reduce into the identity component. So let's suppose, by way of contradiction, that it did. So that would mean that x and infinity have their same reduction at p. But then the same argument, that would say that f of x is equal to f infinity in A of fp. And that would say that f of x is equal to f of infinity in A of z 1 over n. And that would imply that f of infinity is f of 0. And we're assuming that that's not the case. That's a contradiction. Okay? And so just like in step 2, we get the same corollary here. If P is a prime of bad reduction, then E of n splits. Okay? All right, so now we can complete the proof. All right, so let gamma be the absolute Galois group of Q. Let rho be the representation corresponding to the n torsion. So this is given by En, and let K be the cyclotomic field. Q would join the nth roots of unity. So first I want to say that rho is unramified over K. So we're going to consider 3 cases. So we have to show that for every prime of K, the representation is unramified at that prime. And we're going to consider the rational primes that the primes of K lie over. So first, let's consider primes, rational primes P not equal to n, where E has good reduction. So if P is not equal to n and E has good reduction, well, we just know that in that case, the n torsion of E is just unramified as a representation without even going to K. Right? That's the easy direction of Naranov-Shafarevich. So that's the easiest case. Now suppose that P is equal to n and is a prime of good reduction. Okay, so since E has good reduction at P, the n torsion of E, this is a nice finite flat group scheme over Zn. And we know that we have a sequence like this. Because we know that we have an endpoint of E. So this is an exact sequence of finite flat group schemes. And the point is that we also have the connected Ital sequence for En, and that goes, and that flips things around. And so that forces a splitting. So this is split. Since the connected Ital sequence goes the other way. But the connected part of En is going to be mu n, and so that's going to say that mu n sits inside of En. So En is equal to z mod nz plus mu n, which says that when you restrict to QP, the Galois representation rho is the sum of trivial and cyclotomic. And so when you go up to K, it's the trivial representation. also in particular unramified. And then the same thing happens at the primes of bad reduction, because there we know that you already have this direct sum. So steps 2 and 3 imply that En is already split. Okay? So now we're just going to use the fact that this row is very special to prove that it's pretty trivial, that it's split. So rows of the form, it has the following form. So here chi is the mod n cyclotomic character. So, I mean, rho is the representation on the n torsion. So there's a rational point of order n, that means there's a fixed vector. That explains the first column. And the determinant is cyclotomic by the Weil pairing, so there's a chi here. And then there's just some other thing here, this f0. So this f0, you can think of as a map from the Galois group to Fn, and it's a 1 cocycle for chi inverse. Chi inverse. Okay, so if we, let me define f to be the restriction of f0 to k. So f is actually a homomorphism. It's a group homomorphism, because when I restrict to k, this cyclotomic character becomes trivial. So I have a representation like 1f1, right? And that means that f is a group homomorphism. So f is a group homomorphism from this gamma k to Fn, and by the previous proposition, it's everywhere unramified. I mean, that doesn't really matter, but if you wanted to classify extensions like this, it'd be like, I think it's h1 of chi. I mean, just it satisfies the 1 cocycle identity. That's what you need for it to be a representation. Okay, so the restriction of f0 to k, we know it's everywhere unramified by that proposition, and it's actually a homomorphism, just by the form of rho. So it factors through the abelianization of gamma k, and even the quotient, of course, it's everywhere unramified. By global class field theory, that's the class group of k. So we can regard f as a homomorphism from the class group of k to Fn. And so it actually factors through the quotient, the quotient of the class group by n. So I'm going to call that h. So let me call h the class group of k tensored with z mod nz. So this is a vector space over Fn. And I can think of my f as an element of the dual space. Right, it's a map from h to Fn. So the Galois group of k over q, which is Fn star, right, this k is just the adjoining nth roots of unity. The Galois group is Fn star. This acts on h. So h is an Fn vector space, and this group is primed to n. So I can decompose it into the irreducible actions of this Fn star. And the irreducibles are just the characters of the group, so just given by kind of powers. So if I let hi be the subset of h, where, let's say, sigma in here acts by this is bad notation. So maybe for an element a in here, I'll write bracket a for the Galois thing. So I want a acting on x to be a to the I times x. So this is just the isotypic piece of h corresponding to this character of the Galois group. And what I was saying is because the order of the Gal group is invertible, H decomposes as the sum of these HIs. Okay, and of course, you can do the same thing on H star. And if you look at, this one cocycle that F0 satisfies, that tells you how the Galois group acts on F. And if you actually write it down carefully, you see that F is an element of H dual 1. If you act on F by an element of Gal K over Q, you just get chi popping out. And this H star 1 is the same thing as H minus 1 star. And now we need to use Herbrand's theorem. So this is just a theorem in algebraic number theory. It tells you something about these H's. And so the exact statement is the following. At least this is a part of it. So suppose that J is an odd integer greater than 1. Then the jth piece of H is non-zero only if n divides the Bernoulli number Bn minus j. Okay? So I'm just going to use this as a black box. Okay, so we're interested in H minus 1. So H minus 1 is the same thing as H n minus 2, because these numbers are only defined mod n minus 1. And so n minus 2 is an odd integer, because n is odd. And so this is non-zero only if, I guess I should say corollary, H minus 1 is non-zero only if n divides B n minus 2, which is 2. And what is B2? It's 1/6. But B2 is 1/6. So nothing divides that. So this implies that this H minus 1 is always 0. That means that our F is 0. So if I look at the restriction of rho to k, by definition this is 1F1, but we just shown that F is 0. That's what this Herbrand's theorem implies. So this is just a trivial thing. So restricted to k, rho is the trivial representation. So this means that we can regard rho as a representation of the Galois group of k over q. And this is prime to n. It's an Fn representation of this thing, so it's semi-simple. So that gives us the splitting. Right. Are there any questions? Where? You mean why is F in H1 or H minus 1? Oh, I'm restricting to K, right? Restriction of chi to K is. Any other questions? All right. So from now on, we're going to be working to construct, I guess for the next maybe 3 or 4 lectures, construct our F and A so we can actually apply this theorem.